You ever see the incredible sparkle of a diamond? Or maybe a shimmering mirage on a hot road that looks just like water? Well, that's not magic. The secret behind both is actually a surprisingly simple and honestly beautiful science: ray optics.
So here's our game plan. We're going to trace the path of light right from the beginning. We'll start with the basic rules, then figure out how to trap light, which is cooler than it sounds, and finally, we'll see how we engineer the perfect image, the kind that lets us stare into the farthest corners of the universe.
All right, let's start with a concept that's just beautifully simple. For all its mystery, we can think of light as traveling in perfectly straight lines or rays. That one idea, that's our foundation for everything. And yeah, that's the official definition. But all it really means is that as long as light is moving through one thing, like air or water, it goes straight. This one simple assumption is the key that unlocks pretty much everything else. It's rule number one in the optical playbook, and it lets us predict exactly what mirrors and lenses are going to do. Now, this is where it gets really interesting. Check this out. These are the core formulas for mirrors and lenses. They look almost identical, right? They connect the focal length f to the object's distance u and the image's distance v. But look closer. The only difference between a mirror reflecting light and a lens bending it is a single plus or minus sign. That's it. One tiny symbol separates two completely different worlds of optics. Wild, huh? And here's one of those rules in action. Any ray of light coming in parallel to that center line, we call it the principal axis, is always going to be bounced through one special spot, the focal point. It's like a target that the mirror forces all that parallel light to hit. No exceptions. Okay, so we know light can be reflected, it can be bent, but what if we could use those same rules to do something really amazing? Not just redirect light, but trap it completely. I know, it sounds like something straight out of science fiction, right? But physics has this incredibly elegant answer that doesn't just exist. It actually powers our modern world. So what is this crazy effect? They call it total internal reflection. You can think of it as a perfect one-way door for light. Once you get the conditions just right, light hits a boundary, and instead of passing through, it reflects back perfectly. It's literally trapped. It can't get out. And this light trap has a very specific two-step recipe. First, the light has to be going from something dense, like water, into something less dense, like air. Second, it has to hit that boundary at a really shallow angle, an angle greater than what we call the critical angle. You meet both those conditions, the trap snaps shut. The light is perfectly reflected back inside. And this effect is absolutely everywhere. That sparkle in a diamond, that's light getting trapped inside, bouncing off the internal facets over and over again before it finally escapes. A mirage in the desert, same thing. Hot air near the ground is less dense, so light from the sky bends and reflects up, fooling your brain into seeing water. And maybe most importantly, this is the engine of the internet. Light pulses are trapped inside fiber optic cables, bouncing for thousands of miles to bring data right to your screen. Okay, so we've got the rules for how light travels and even how it can be trapped. So how do we actually use those rules to build the tools that shape our world? Like lenses. This right here is the lens maker's formula. Think of it as the master recipe for making a lens. It connects everything. That Greek letter mu stands for the material's refractive index, basically how much it can bend light. And R1 and R2 are just the curvatures of the lens's two sides. With this formula, an engineer can pick the right glass and the right curves to make a lens that focuses light exactly where they want it to go. But, getting that recipe right is all in the details. As you can see here, these sign conventions are absolutely critical. Whether a surface curves out or in determines if its value is positive or negative. You get one of those signs wrong, and the math spits out a totally different lens, one that might scatter light all over the place instead of focusing it. Now, this powerful formula works so well because, we simplify things just a little bit. We assume the lens is pretty thin, that the opening is small, stuff like that. And for most things, from the glasses on your face to the camera in your phone, these assumptions work perfectly fine and let us design some incredible optics. But what happens when reality isn't quite as neat and tidy as our formulas? What happens when our simple rules actually create imperfect images? Well, this is the story's plot twist, the flaw in the system.
So, an aberration, it's just a fancy word for an imperfection. It's when light rays that all came from the same single point fail to meet back up at a single point after they go through a lens. It's like a ghost in the optical machine, and it's what causes blurriness and distortion. And this right here is a classic example, spherical aberration. Just because of the simple spherical shape of a lens, rays that hit the outer edges get bent a little more sharply than the rays hitting the center, so they miss the focal point. Instead of a sharp, crisp dot, you get a blurry mess. And it's not just one problem. Oh no, lens makers have to fight against a whole family of these flaws. You've got coma, which makes stars look like little comets, astigmatism, which stretches points into lines, and chromatic aberration, which causes those weird color fringes. Each one messes with the image in its own special, frustrating way. So, how in the world do we defeat these villains of the optical world? Well, it takes some of the most advanced and mind-bogglingly precise engineering on the planet. To beat these flaws, engineers at places like NASA can't just use simple round shapes. They use these incredible machines to grind mirrors and lenses into really complex, aspherical shapes. These are custom curves designed with one purpose: to perfectly correct for the errors and make sure every single ray of light lands exactly where it's supposed to. And this isn't about getting a clear picture for your next vacation photo. Like NASA says here, this is a mission. It's about building the tools, like the Hubble or James Webb telescopes, that let us see to the very edge of the universe. It's all about engineering the perfect image to unlock the next great scientific discovery.
So think about it. We've gone from explaining a mirage in the desert to building eyes that can literally watch stars being born. We've learned to master the path of light itself. The only real question left is, what new windows on the universe will we open up next?